Okay, we're in part three of chapter 14 of conceptual physics, and we're going to discuss Bernoulli's principle. And instead of starting off with the PowerPoint as I usually do, I've got a little demonstration here. It's just a little strip of paper. You can do this at home. You take a straw. I've got a straw here and a piece of paper. And certainly, if I put the paper under the straw and blow, we get the expected results. The air is pushing on the paper and it makes it flat. Now, what happens if I put it on top of the paper? Draws on top and it still flies up. And this is part of the Bernoulli effect. With I'm pushing air on the top of it, and so the pressure on top is less, and it makes the pressure from the bottom push the piece of paper up, and that's what we're going to learn about. We're going to learn about Bernoulli's principle. So let's share the screen, and I'll dismiss my image as we continue. Bernoulli's principle is discovered by Daniel Bernoulli, a 15th century Swiss scientist. It states that where the speed of a fluid increases, the internal pressure in the fluid decreases, and vice versa. If the speed of the fluid decreases, then the pressure increases. It applies to smooth and steady flow. Turbulent flow, it's not. It doesn't necessarily apply. Okay, so streamlines. These lines here, these lines are indications of the stream of flow. They're simply representative. They don't exist, but you can think of this laminar fluid flow. Streamlines are thin lines representing fluid motion. Where they're closer together, the flow speed is greater, pressure within the fluids is less. So when you see these things tighten up, that means the flow increases and the pressure increases. Let's think of you're watering your lawn with just a hose. It comes out at a certain rate. You put your thumb over the hose to constrict some of the flow, and it comes out faster. That's you're applying Bernoulli's principle. Where the streamlines are wider, the flow speed is less, and pressure within the fluid is greater. So you can see that here the pressure is greater. These little air bubbles are small here. The lines are closer together, so the fluid flow is faster, and these bubbles are bigger because there's less pressure. Okay, so volume 1 times area 1 equals volume 2 times area 2, so that if the area constricts, the volume increases. So this is a good formula to remember. Volume 1, area 1 is equal to volume 2, area 2. So if you constrict the area, the volume increases. Okay. Laminar flow is smooth, steady flow of constant density fluid. Turbulent flow, the flow speed above a critical point becomes chaotic. It's not laminar. You get all sorts of eddy currents and stuff in the flow. Eddy currents are the little swirls, like little whirlpools. Okay. The pressure in a stream of water is reduced as the stream speeds up. Can a stream of water from a fire hose knock a person off his or her feet? Okay, so we said if it speeds up, the pressure is less. Well, that's the internal pressure. So it can't, as Bernoulli principle illustrates, well, Bernoulli's principle is for the internal pressure, not the pressure of it coming out the front. It can and is consistent with Bernoulli's principle, yes. Bernoulli's principle works only for laminar flow, which is the stream is not. No, it is laminar flow. And D is none of the above, so it's B, it can and can, it's consistent with Bernoulli's principle. There's a difference in the pressure within flowing water and the pressure it can exert when its momentum is changed. The pressure that knocks one off his feet or her feet is due to the change in the water's momentum, not the pressure within the water. Again, Bernoulli's principle applies to the internal pressure of the water, not the pressure that it's coming out. That's the momentum that it's coming out with. Applications of Bernoulli's principle. Blow on the top surface of a paper and the paper rises. I demonstrated that at the beginning of the lecture. The reason the pressure of the moving air is less than the atmospheric pressure beneath it. When I blow on top of the paper, the pressure is less than atmospheric pressure, so it pushes the paper up. A convertible car roof puffs upward as the air moves over its top surface. Another thing, if you're riding along at 60, 65, 70 miles an hour, going the speed limit, if you just roll your window down just a little bit, you'll feel the pressure on your ears because you're going at a high rate of speed. The pressure on the outside of the window is less, so that when you open the window, you'll feel the drop in pressure on the inside of the car. Let's get back to the reason for the convertible car roof. Pressure of air moving on the top surface is less than the atmospheric pressure inside the car. Same thing with opening your window. Where the pressure on the outside of the window is less than the atmospheric pressure in the car, you open the window, you'll feel the pressure decrease, and you'll typically feel it in your ears. Okay. Wind blowing across a peaked roof can lift the roof off the house. The reason the pressure is reduced as wind gains speed as it flows over the roof. The greater pressure inside the house lifts the roof up. Perfume atomizer, and I've got a little graphic here in a little bit. The reason air rushes, let me go down there so we can see there's the atomizer. He's got the plunger just like I showed in the when I opened up with Boyle's law. It's got a little plunger. As you push air over this over this tube, the pressure is less over the tube, and the atmospheric pressure, you can see it's open here, the atmospheric pressure pushes the fluid out and is caught by the airflow, and it sprays. Now let's go back to the atomizer. Air rushes across the open end of the tube when you squeeze the bulb, reducing pressure in the tube. Atmospheric pressure on the liquid below pushes it up into the tube, and you get your spray, your perfume atomizer. Okay, trucks passing closely on a highway are drawn to each other. Reason the air pressure between the trucks is less than the pressure on the outer sides pushing inward. It's the same with ships. The risk of passing ships colliding sideways. The water pressure between the ships is less than the pressure on the outer sides of the ships, which pushes them inward and towards each other. And they show a little experiment here with two little toy ships anchored. And if you run water through it, it'll draw them together. Let's go back to I think, yeah, water pressure between the ships is less than the pressure on the outer sides pushing inward, so there's risk of them colliding. And here's a little graphic of an airplane wing. Their shape is like this. You have air being deflected downward, and the air going over the curved portion of the ring goes faster. And so the pressure, since the air is moving faster here, the pressure is left, and that causes lift. And this little red vector is the drag force. So this is the lift force, and this is the drag force. So the air moving over the wing, the sloped wing, it moves faster than the underside of the wing, and that since it's faster, the air pressure is less, and that causes lift. You can see that the same thing is true of the airplane propeller. They're shaped like this, so that the propeller, some people think of it just as a fan and it moves. Well, it's also this pressure gradient. The airplane propeller, there's less, the pressure is less this way, and that helps move the plane forward. Okay, and this is the curved ball. This is a ball going without any spinning, and it, basically you have laminar flow of the air going across it. But if you have spin in it, it's what you call the Magnus effect. If you look up Magnus effect, I'll probably post a video on Canvas to show you. If you can look up Magnus effect, and you'll see people tossing a basketball off a bridge, and if you just drop it, it'll just drop straight down. But if you spin it, like where the spin is going underhand, you'll see that the basketball just takes off in a forward motion. That's the Magnus effect, and it's the same thing here. You've got this the fact that whether it's the stitching on a baseball or the fuzz on a tennis ball, the spinning will cause a force to one side and causes it to curve. And that's the atomizer, and that's the boats. And this is a young lady holding a balloon. As the balloon goes forward, as the car goes forward, her head is thrown back, but the balloon goes forward. Well, that seems counterintuitive. It seems like if her head goes back, the balloon should go back also, but that's not. What's really happening is that the balloon is less dense than the surrounding air in the car, so it's the air that when the car moves, and just like her head goes back, the denser air goes back and pushes the ball forward. Let's see if it's, there's the end. Instead of just ending the lecture, I'm going to stop the share. And if you have a little level like this, you can do this experiment. I don't know that you can see it on the screen. It's probably not detailed enough. But if I push it, it seems to go opposite what you would expect it to. If I push it in this way, the bubble goes forward. You would think it would go backward, but the bubble is empty space. The fluid is more dense, so then when I push it this way, the fluid wants to go back, which pushes the bubble that way. So you can just, if you have a level at home, just play with it and move it in the direction, and you'll see that in either direction, you see that the bubble moves in the direction that you're going, not opposite, because the heavier fluid is moving backward. And I think that's it for this. It's the end of part 3. We'll finish up with plasmas. Okay.